In this video, we're going to talk about the SI base units and also some derived units. Now, the SI base unit for length is the meter. You can convert the meters into kilometers, feet, inches, centimeters, miles. There's many different units of length, but according to the International System of Units for length, the standard unit is the meter. For mass, it's the kilogram. Standard unit for time is the second. For temperature, it's Kelvin. For quantity, it's the mole. For electrical current, it's the amps. And for luminous intensity, it's candela or CD. Now let's talk about length first. Here are some common conversion factors that you want to be familiar with. 1 kilometer is equal to 1,000 meters. 1 meter is equivalent to 100 centimeters. 1 mile is equal to 1.609 kilometers. And 1 mile is also equal to 5,280 feet. Now, there's 3 feet in 1 yard, and there's 12 inches in a foot. And 1 inch is equal to 2.54 centimeters. So when dealing with length, those are some common conversion factors that you want to be familiar with. When dealing with mass, the most common conversion factor you'll typically need is this one. 1 kilogram is 1,000 grams. In chemistry, a lot of times you'll be dealing with grams when it comes to mass, but in physics, you'll typically deal with kilograms in regards to mass. Now, for both chemistry and physics, the most common unit of time that you'll be using is the second. As you know, there are 60 seconds in 1 minute, and there's 60 minutes in an hour. There's 24 hours in a day, 7 days per week, an average of 30 days per month, and 1 year is equal to 365 days. By the way, a light year is not a unit of time. Rather, a light year is a unit of distance. Now let's move on to temperature. If you want to convert from Celsius to Kelvin, you could use this formula. The Kelvin temperature is the Celsius temperature plus 273.15. And if you want to get the Fahrenheit temperature from Celsius, you could use this equation. It's 1.8 times the Celsius temperature plus 32. Now, whenever you see the mole represents a quantity, which typically used in chemistry. Think of the word dozen. A dozen is equal to a specific number, 12. If you have a dozen eggs, you have 12 eggs. If you have a dozen calculators, you have 12 calculators. A mole also represents a quantity, but it's a large quantity of something, specifically 6.02 times 10 to the 23, which is also known as Avogadro's number. So if you have a mole of books, you have 6 times 10 to the 23 books. If you have a mole of pillows, you have 6 times 20 times 10 to the 23 pillows. So a mole is just a very large quantity of something. Now, electric current. The unit for electric current is the amp. And I'm going to talk more about that a little bit later in this video. First, let's go over something called a derived unit. Velocity. Velocity and speed, they have the same unit. Velocity is displacement over time. Speed is distance over time. Displacement has the units meters, and the base unit for time is seconds. So for velocity, the derived unit is going to be meters per second. Now, what about acceleration? That's a very common topic in physics. Acceleration is the change in velocity divided by the change in time. Velocity is typically measured in meters per second and time is in seconds. So when you take meters per second and divide it by seconds, you get meters per second squared for the derived unit for acceleration. Now let's move on to the next physics topic, force. What can we say about force? According to Newton's second law, force is equal to mass times acceleration. The standard unit of force is the Newton, but it's basically a derived unit. So force, which is measured in newtons, is equal to the mass, which is measured in kilograms, times the acceleration, which is meters per second squared. So 1 newton is equal to 1 kilogram times 1 meter per second squared. So that's the equivalent derived unit of force. Now we talked about length, which is in meters. Area is square meters. So think about if you have the area of a rectangle, it's length times width. The length of the rectangle can be measured in meters. The width can also be measured in meters. When you multiply meters by meters, you get square meters. Now, area could be also in terms of other units of length. It's length squared. So you could have square feet, square yards, you could have square inches, square kilometers, square miles, acreage. An acre is a unit of area. Now, volume, if you think of a volume of a rectangular prism, it's length times width times height. So when calculating volume, you're multiplying meters by meters by meters. So you get cubic meters. In physics, you'll typically see volume in terms of cubic meters. In chemistry, you'll typically see it reported in liters. So it's good to know the conversion between the two. To make space, I'm just going to get rid of this. 1 cubic meter is equivalent to 1,000 liters. And 1 liter is equal to 1,000 milliliters. And 1 cubic centimeter is equal to 1 milliliter. So in chemistry, you'll see volume typically reported in liters, milliliters, or even cubic centimeters. In physics, volume is typically reported in cubic meters. So it's good to know that. Now, let's talk about pressure. What can we say about pressure? Pressure in physics is force divided by area. So imagine applying a force over an area, you're applying pressure to that area. Now, pressure is measured in pascals in physics. Force we know is newtons, area is square meters, so 1 pascal is equal to 1 newton per square meter. Now, in chemistry, pressure is typically measured in atmospheric pressure, ATM. Sometimes you'll see it measured in the unit torr or millimeters of mercury. So here's the conversion for those of you who want to know. 1 ATM, this is pressure of air at sea level, 1 atmospheric pressure. That's equal to 101.3 kilopascals. So if you want to convert this to a unit in physics, that's 101,300 pascals. Now 1 ATM is also equal to 760 units of torr, which is also equal to 760 millimeters of mercury. Mercury is typically used to measure pressure in certain devices. So that's why you'll see it reported as a unit. Now, the next derived unit that we're going to talk about is density. Now, density is equal to mass divided by volume. In chemistry, the mass is typically in grams. The volume can be in cubic centimeters or milliliters. So in chemistry, you'll see the density reported as grams per cubic centimeter or grams per milliliter. In physics, the mass is usually reported in kilograms, and the volume is typically reported in cubic meters. So in physics, you'll see density as kilograms per cubic meters. Now here's the conversion between the two. So because milliliters and cubic centimeters are the same, these two units will have the same value. But these two units differ by 1,000. So for instance, the density of aluminum, in chemistry, you'll see it as 2.7 grams per cubic centimeter. In physics, this is reported as 2,700 kilograms per cubic meter. Now keep in mind, a kilogram is 1,000 grams, but a cubic meter is 1 million cubic centimeters. When you have a million divided by 1,000, you get a multiplication factor of 1,000. So if you look at these two, 1 cubic meter is 1,000 liters, and 1 liter is 1,000 milliliters. So a cubic meter is a million milliliters, which is equivalent to a million cubic centimeters. And 1 kilogram is 1,000 grams, so when you divide a million by 1,000, you get 1,000. So that's why these two differ by 1,000. Now, the next thing we're going to talk about is something called work. And we'll also talk about energy. Now, work and energy, you can measure them both with the same unit, and that is they're typically reported in a unit of joules. Now, there are other units that represents energy. Energy can be represented in calories. There's also kilocalories, and there's also electron volts. These are other units of energy. The most common unit of energy that you'll typically see is the joule. Now, work is equal to force times displacement. Force is measured in newtons, displacement is measured in meters. So what this means is that 1 joule is equal to 1 Newton times 1 meter. Now, there's other ways to describe energy as well. For instance, if you think about this formula, kinetic energy, it's 1/2 mv squared. The mass is in kilograms. The speed is meters per second, but it's squared. And that's going to be equal to a joule. So we can also say that 1 joule is equal to 1 kilogram times a square meter divided by a square centimeter. Divided by a square second. So a joule is equivalent to those units as well. Now let's talk about the conversion between these two, for those of you who are interested. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. Now, when dealing with thermal energy, particularly heat, you'll see calories and kilocalories typically represented as a unit of energy. So 1 capital calorie is equal to 1,000 lowercase calories, which is equivalent to 1 kilocalorie. And 1 lowercase calorie is equal to 4.184 joules. This is based on the specific heat capacity of water. The specific heat capacity of water is 4.184 joules per gram per Celsius. That's where the unit calorie comes from. It's how much thermal energy can be stored in water per degree Celsius per 1 gram of water. So here's what it means. Let's say if you have 1 gram of water. I'm going to draw a picture. So because the density of water is 1, this is equivalent to a milliliter of water. So we have 1 gram of H2O. And let's say the temperature of this sample is 25 degrees Celsius. It's going to take us 4.184 joules of heat energy. If we apply this amount of heat energy to 1 gram of water, the temperature of that sample of water will increase by 1 degree Celsius. So it's going to go up from 25 to 26 degrees Celsius. That's the basic idea behind the specific heat capacity of water. It tells you how much energy water can absorb in order to increase its temperature by 1 if you have 1 gram of water. So water can store a lot of energy. The specific heat capacities of metals is much lower than this number. So water can store a lot of thermal energy before increasing its temperature by 1 degree Celsius. It has a very high heat capacity. Now, the next unit we're going to talk about is power, or rather, the next thing we're going to talk about. Now, power is a rate. Before we talk about power, work and energy, even though they look similar, they're not the same. Energy is basically something that is possessed by something. So, for instance, a ball can have energy. A ball that's moving has kinetic energy. A ball that's on a hill has potential energy. So, a ball can possess energy. However, a ball can't possess work. So, work and energy are not the same. Work is more of a mechanism. It's a mechanism by which energy is transferred. So, if you were to apply a force, let's say on this block, you can increase the kinetic energy of that block as the block begins to move from rest. So that force is doing work on that block. It's increasing the block's kinetic energy. Because as the block speeds up, the kinetic energy will go up. So that force is doing work on a block by transferring energy from one object to another. So let's say if a ball strikes that block. When the ball strikes the block, the ball's going to slow down, but the block's going to speed up. Energy is transferred from the ball to the block. So the ball is doing work on the block. So work is really a mechanism by which energy can be transferred. But they can both be represented with the same units, which is joules. Now, power is the rate at which energy is transferred. So power is work divided by time. Because you could transfer the energy in a slow rate, or you could transfer the energy at a very high rate. So power tells you how fast that energy is being transferred. The unit of power is the watt, which is equal to joules per second. So 1 watt is 1 joule per second. A horsepower is a typical unit of watts. 1 horsepower is 746 watts. So if you think about what that means that 746 joules of energy is being transferred every second. So let's say if you have a car that has an engine that can generate 300 horsepower. If you multiply that by 746, that's 223,800 watts. So this engine, or this car with an engine of 300 horsepower, can transfer 223,800 joules every second. That means in 10 seconds, it could transfer 2.2 million joules of energy. So I want you to understand that concept. Power is the rate at which energy is being transferred. So 1 watt is 1 joule per second. And it's good to know this one as well. A kilowatt is 1,000 watts. Now, when dealing with electricity, there's a unit called kilowatt hours. If you look at your electric bill, you'll see this. Now, don't get confused between kilowatts and kilowatt hours. Kilowatt is a unit of power, so I'm going to put that here. Kilowatt hours is a unit of energy. Remember how we said that power is work over time? You can also describe power as being energy over time. Energy and work, they're related to each other. They have the same units. If you solve for energy by multiplying both sides by t, you get that energy is power multiplied by time. So the power can be in kilowatts. Hours is a unit of time. When you multiply power by time, you get energy. Therefore, the kilowatt hour is a unit of energy and not power. So make sure you understand that difference though. So if you see kilowatt hours, that is a unit of energy. If you see kilowatts, it's a unit of power. Now let's talk about momentum. Momentum is basically mass in motion. It's represented by this symbol, lowercase p. It's mass times velocity. Mass is in kilograms, velocity is meters per second. So momentum is just kilograms times meters per second. Now there's something called the impulse momentum theorem. Impulse, let me say that again. Impulse is force multiplied by time. The impulse is equal to the change in momentum, mass times the change in velocity. So force is in newtons, time is in seconds, mass is in kilograms, v is in meters per second. So momentum can be represented as kilograms times meters per second, but it can also be represented as newtons times seconds. So that's why I wanted to mention the impulse momentum theorem. So you know that those two units are equivalent to each other. Now let's talk about frequency. You're going to encounter this topic when dealing with waves. It could be light waves, sound waves, or even simple pendulum. Frequency is equal to 1 over the period. The period is the time it takes to complete one cycle. The frequency is the number of cycles that occur per second. The frequency is measured typically in hertz. So imagine having a 1 kilohertz sound wave or a 500 hertz sound wave. Hertz is the unit of frequency, and period is measured in seconds. So 1 hertz is equal to 1 seconds to the minus 1, or 1 over seconds. Now let's talk about electricity. So we said that the SI unit for electric current is the amps. The unit for electric charge is the coulomb. So think of how moles represents the quantity of something. Electric charge represents the quantity of charge, or the total quantity of charged particles. But it's more accurate to say the total quantity of charge, because some particles can have more charge than others, so it really represents the quantity of charge. Now, Q is equal to IT. Q is the charge measured in coulombs. I, in physics, is the electric current measured in amps. Time is in seconds. So if you solve for I, you get Q over T. So what this means is that 1 amp of current is equal to 1 coulomb per second. So electric current is the rate at which electric charge is flowing through a circuit. Much the same way as power is the rate at which energy is being transferred. So electric current tells you how much charge is flowing through a wire at any given second, or rather, per second. Now, electrical resistance. Resistance is measured in ohms. So we have V is equal to IR. If you solve for resistance, it's voltage divided by current. So 1 ohm is basically 1 volt divided by 1 amp. Electric potential is measured in volts. Voltage is electric potential difference. If you have 2 points and you know the electric potential between, if you know the electric potential of both of those points, the difference in that potential is voltage. So just to illustrate that concept, let's say this is point A and this is point B. Let's say point A has an electric potential of 300 volts. Point B has an electric potential of 500 volts. Now, these two values, they don't represent voltage. They represent electric potential, and it's specific to a point in space. Voltage is the difference between those 2 points. So voltage is electric potential difference. The voltage between those 2 points is 200 volts. So when dealing with voltage, you need to compare the electric potential of 2 points. If you just have 1 point, you're talking about electric potential and not voltage. However, both electric potential and voltage, they have the same unit, which is the volt. Now, electric potential, represented by the symbol V, is equal to potential energy divided by the charge. So electric potential is the ratio of potential energy to charge. So 1 volt means that you have 1 joule of electric potential energy per 1 coulomb of charge. 100 volts can mean multiple things. It can mean that you have 100 joules of electric potential energy per 1 coulomb of charge, or it can mean that you have 1 joule of electric potential energy per zero point zero 0.01 coulomb of charge. There's many ways in which you could see that. So that's electric potential. It's the ratio of energy to charge. So voltage, the unit volt, that is a derived unit. Velocity, acceleration, force, those are derived units. But the first 7 that we went over, those are the SI base units, like the meter, the kilogram, the second, the mole, Kelvin, amps, candelas. Those are the 7 common SI base units. So that's basically it for this video. Hopefully it gave you a good introduction into SI base units and derived units. Thanks for watching.